If you've been watching my channel for a while, you know that one of the greatest concerns in human space exploration on the moon and Mars is dust. This stuff is spiky, sticks to everything, is electrostatically charged. It gets everywhere. It gets inside astronaut lungs. It gets into all the equipment and machinery. It coats solar panels, coats radiators, coats cameras. It is a big problem that people are trying to work out. It has ended the life of many rovers and landers on the surface of Mars. And so coming up with a solution for dust is a top priority for NASA. And whenever we talk about how dust has ended another mission on the moon or Mars, people start to hit me with the why don't they just have little windshield wipers? Why don't they just tilt the solar panels? Why don't they shake the solar panels? Why don't they have some kind of electrostatic shield that pushes the dust off of it? And I promise you, NASA is trying to figure out these solutions. They've tried all these ideas, and in the end, the one that was the most weight efficient was to just let the rovers eventually die. But work is ongoing, and there have been a ton of really interesting new materials that are developed where you are essentially taking advantage of this electrostatic charge that the dust particles have and use that to gently guide it in directions where you want it to go. My guest today is Luca Scifoni. He's a PhD student in the School of Aerospace Engineering at Georgia Institute of Technology. He's part of a team that is working on new kinds of materials that will allow you to run an electrical current through the outer surface, and this will then cause the dust to be pushed off as if water is flowing across the surface, washing it away. They've got some interesting prototypes they're working on in the lab, and maybe someday we will see this fly on a mission to the moon. But in fact, there has already been a version of this that has been tested out with the Firefly Aerospace Blue Ghost mission. And so you can see this is a top priority for NASA. So if you're interested, if you've ever thought, why don't they just... this is probably the interview for you. Enjoy this conversation with Luca Scifoni. Luca, have you had a chance to actually hold real lunar regolith in your hands?
Unfortunately, I have not. I've had the opportunity to see it, but never to touch it. What we use in our research is a simulant that is very similar, and I would also say almost equally dangerous, but no, I haven't had the chance to see, but not to touch the real one. Yeah.
Right. Yeah. There was a moon rock at the Kennedy Space Center. There's like that big rocket at the Kennedy Space Center, and there's a moon rock. You can come up and you can actually touch the moon rock.
We also have a piece of moon rock here at Georgia Tech, and there is this like place where you can go and touch the moon, and it's very, very cool, but it's not dust. It's a rock, lunar rock. Yeah, very similar.
Yeah. But when you put either lunar dust or the simulated lunar dust under a microscope, what are you looking at? What do you see?
So you usually see very sharp and angular grains. You can clearly understand that it's not the same as the dust or other particles like sand that you can find on Earth. And this is mostly because you don't have atmospherical effects on those dust particles. So you usually see those very irregular geometries. And this is something that increases a lot the complications that lunar dust introduces in lunar mission, but also, I would say, in our understanding of it. Because, it's always easier if you can model something like a spherical particle or as a geometry that is not that complex, that complicated. And so the fact that it is so angular and so pointy, it's a very big deal, big issue.
Right. And so the different chunks will stick to each other, and it doesn't flow in the way that, say, sand will flow through your hands or something with like even spherical. I don't know. There's like you can sometimes buy like stuff that flows really smoothly in your hands. Yeah.
It's very prone to create agglomerates and those kind of structures. Yeah.
Right. And so, I mean, this is an issue that was revealed as far back even as the Apollo missions, where the Apollo astronauts realized that this stuff was getting everywhere and was making them cough. Do we have a better sense now of what are the implications of this lunar regolith on people, machinery, things like that?
Yeah, definitely now we have a sense of it. We know that it's one of the biggest issues that we can have. I think that people out there don't really understand, because it's not easy to understand it, how problematic it is. But I always like to think about the fact that we have only been on the moon for like 12 days, something like that, if you sum all the Apollo missions together, and less than a quarter of that was extravehicular activity. And the longest mission was Apollo 17, 3 days more or less, with 1 day total of extravehicular activities. And it was enough to send them crazy about the dust. If you read the things that the astronauts from Apollo 17 said about the lunar dust, for example, the commander, Eugene Cernan, he said that we can probably overcome all the mechanical, physical, and psychophysical challenges associated with lunar exploration, but dust will be the worst one, will be the last one that we will be able to tackle completely. And so now that we know it, we know how problematic the lunar dust is, how many issues it causes. We have been studying methods and ways to mitigate its effect for the past 50 years. And yet we're still here in 2025, and we talk about lunar dust as one of the biggest technology gaps that we have. So yeah, we have a sense of it. This summer I was at the NESF conference in Albuquerque, and there was Jake Bleacher, one of the chiefs of the Artemis mission. He was giving us some updates about the Artemis missions, and there was this list of technological gaps. And the issue number one was lunar dust. Finding dust-tolerant systems and mitigation method that can help us. So yeah, now we know how many problems it can cause, but we are still working on finding a way to avoid and mitigate all these issues.
And what do the mitigation strategies generally break down into?
We usually divide the mitigation strategies in passive and active approaches, depending if you use or you don't use an external energy source. There are very cool passive methods out there, for example, coatings. One of them is the lotus leaf coating that has been designed to create this super hydrophobic surface on which the dust doesn't really stick, or at least is easier to remove after sticking on it. But we have to take into account that dust is moving all around on the lunar surface. There are transport mechanisms, there are a lot of things that can alter the dust movement. And we have to be ready to face also more problematic situation with a lot of dust coming to the device that you want to protect or the astronaut that you want to protect. So having a passive method cannot always work, and you need an active way of removing the dust. Something that you can use when you say, okay, now this solar panel is completely covered with dust. What can I do about it? How do I remove all the dust on it? And so the cool thing about the electrostatic or electrodynamic methods is that you take what is one of the biggest issues related to the lunar dust, that is the fact that it's electrostatically charged, and you use it your way. You use it to repel that dust. So the way we repel the dust is to create non-uniform electric field that interact with the dust particles that are charged and send them away using basically the Coulomb force. So the basic force that an electric field exerts on a charged particle. Of course, this is not easy to implement, not always easy to implement, but the concept is very, very easy. The devices that we have designed, that actually have been designed over the past 20, 30 years at NASA, for example, at the Kennedy Space Center with Dr. Kaye, who worked a lot on this topic, they're based on a very simple concept. They are called electrodynamic dust shields, and they use an array of electrodes that is usually an array of 2 or 3, even 4 electrodes that are interdigitated. So they are intersecting one with another without touching, but just being very, very close, and you apply a waveform signal to each of the electrodes with a phase shift between one electrode and the other. And in this way, you can create this non-uniform electric wave, we call it an electric wave, that interacts with the dust particles. You can have a design that is more and more complex depending on the number of electrodes that you use. If you just use 2 electrodes, you have a phase shift of 180 degrees, and you generate a standing wave. So just an oscillating electric field on top of your device, on top of your surface. And in this way, the particles go all around. So they can go back, forth between the electrodes, but at a certain point, you will be able to remove all the particles from a surface. If you use 3 electrodes, you generate what is called a traveling wave. So you have a net direction in your dust transport. You can move the dust from one point to another in a straight direction.
So let's say you take a material, a solar panel, whatever, and you have this either the double or the triple
phase.
What phase on it? 2
or 3
and
phases.
Then you run the electricity through it. What does it look like? What happens?
It's very, very cool. You see the dust particles. I can make you the example of a 3-phase device. Imagine to have this array of electrodes on top of a surface, and as soon as you activate the device and you provide the electricity, you apply a potential to the electrodes, and you change, this is something that I haven't said, you change the phase every 10 times per second or 100 times per second, you start seeing the particles hopping from one electrode to the other, one after the other, one after the other, until the end of the surface. So in about 10 seconds, you can clear like a 10 centimeter surface.
And so, like, when I think about dirt, often it's a little bit mixed with water, leaves a kind of residue, but on the moon, you're not getting that water residue. It's just purely mechanically arrived onto your surface. And how effective is it? Like, does it get all of it off?
It mostly depends on the size of the particles. This method is particularly effective. I mean, it's very, very effective above 20 microns as characteristic size of your particle. But this is just because of the electrode width and interdistance and pitch between the electrodes that you can produce. If you can make the EDS with much smaller electrodes and closer electrodes, you can apply the same technique, the same methods to smaller particles. And yeah, as soon as your particle is large enough, you can always move it. The only thing that you have to consider is that the particle has to have at least a little bit of charge. So the cool thing about this method, as I said, is that you use the fact that the dust particles are charged, and on the moon they are charged because of UV radiation, solar wind, but you actually just need a little bit of tribocharging. And the dust particles on the moon always have a little bit of tribocharging because, for example, they have been moved by the wheel of a rover or have interacted with each other. So you just need that little bit of charge to start the dust motion when it's stuck on the surface. So yeah, this is the only thing that you need. There is actually also another force that is coming into play that is called the dielectrophoretic force and can move a little bit the particles even when they are not charged. You just need to have a different material than the material outside, than the environment, and to apply a non-uniform dielectric field. But in this case, this is exactly what we're doing. So with this dielectrophoretic force, we are able to displace a little bit the dust particles even when they are not charged. And usually this is enough to move them a little bit, displace them, what is enough to overcome the adhesion forces between the dust particles and the surface. And then with even a very, very small Coulomb force exerted by the electric field, we are able to move them. So yeah, it's very, very effective. You can theoretically remove all the particles from your surface. At the same time, when you go to a real device, in a real situation with a finite dimension and a finite pitch of the electrodes, then you always have a certain amount of particles that you're not able to remove. As an engineer, when I see something that cleans 99% of the dust, I'm very satisfied. Like, is a result that I can consider very, very close to 100%. In a more precise way of thinking about everything, we cannot say that we remove all the particles, but the efficiency of this system is very, very high, and depending on the material combination, you can increase it a lot to virtually 100%.
That's amazing. And so what about like weight? How much weight would this add to a surface?
So to talk about that, I have to explain a little bit how the devices are made, because I've explained how the electrodes work, and the electrodes are very, very thin. As I said, they have to be very small, very close, but you need a structure to sustain those electrodes and also to insulate them from everything else that is outside. So you usually have a substrate on which the electrodes are placed or embedded in, and then you also need a dielectric coating. You need something to protect the instrumentation or the astronauts and avoid that they come into direct contact with the electrodes. And you want to avoid the electric breakdown between electrodes. You want to avoid micro-discharge events, so you also need to apply that. But even considering these two things, the substrate and the coating, the weight of these devices is very, very small. They are very light, and also the power consumption is actually very small, because you need to provide a waveform signal to the electrodes, and to do that you need to provide a very high voltage to them, but at the same time the electrodes never touch each other, so it's a pure capacitive load. If you see it as in a pure physics way, like you don't consider any discharge that can happen between the electrodes, the power consumption is theoretically zero. At the same time, you need to have a power system that is able to supply that waveform. That can be a waveform with a peak of 2000 volts, 3000 volts. So the only power that you need is the reactive power that your capacitive loads require, and you need to be able to provide it. But at the same time, you don't have a real power consumption. So it's also very easy to implement them on the moon. At the same time, what is more difficult is to integrate them into the systems. It's easier with solar panels, thermal radiators, anything that is not that the astronauts are not going to directly interact with. But if you think about a spacesuit, then it becomes much more difficult, because you're applying 2000 volts on the arm of an astronaut, and that's, of course, much more complicated.
Right. But in theory, they could take off the suit, and then you could apply the dust in a clean room or something.
That's another opportunity. But of course, the devices work much better when the dust is going on top of them, so on top of this surface, then it's easy to remove it. It's always much more difficult to remove dust that has been already placed on another surface on a spacesuit, for example. That's much more complicated, and probably there are methods that work better for that.
So it's like you need to maintain a voltage potential, but you don't have to actually use a lot of electricity of your power to maintain that. Essentially, I guess whatever is the amount that it's required to actually push the individual particles of dust sideways.
Yeah, if you want to see
electricity is going.
Under an energetic point of view, you could compute, and I think that there is a very cool paper out there doing this. Unfortunately, I don't remember the name of the authors, but they compute the power consumption by computing the energy and the power that you need to move the dust particles, because at the end of the day, it's the same thing. Yeah.
And so this would be very good for the windscreen, the front screen of your rover, or very good for, various, as you said, solar panels that you don't want to have losing their ability to generate power, or radiators that you don't want to be losing their ability to radiate power. That once you move into strange shapes, things that you don't want high voltage potential running through, you're going to need to look at some other solution, but at least that gets you part of the way there.
Yeah. So for the application like viewports, visors, solar panels, you also need transparency. That is another big technical challenge. But what we are focusing more on at Georgia Tech with our material system is to have devices that can be flexible and can conform to different shapes, And we want to do that without compromising the conductivity of the electrodes. Because if you think about using, for example, copper, that is very effective as a material for the electrodes, you have to deal with the fact that if you create a flexible copper-based EDS, after repeated bending, the material of the electrodes tends to crack, is prone to cracking, and the conductivity could be damaged. So to overcome this issue, we are using nanocomposite materials, for example, that help us to realize more flexible devices that can be applied, for example, on, I'm thinking about inflatable structure, for example, or the habitats of Artemis. And those are applications that don't always need transparency, so we don't have that technical challenge, but we can tackle the technical challenge of the flexibility and the repeated bending of the devices.
Now, I know you've been focusing specifically on lunar regolith, but this is a big, or as big a problem on Mars. We see that the dust falling down on Mars saps away the strength of the solar panels on the solar rovers, and on the Martian rovers, and I get all of these "why don't they just" comments from all of the people that are watching my videos. They're like, well, why don't they just put windshield wipers on the thing? Why don't they just tilt the panels over so that the dust falls off? What makes this stuff, this sort of electrostatic charging, what makes it so difficult to work with?
So the first thing that I would answer to your viewers that ask this question is, at NASA, they are so smart that if they knew that there was an easy way to do it, they would have done it already. We have been thinking about solving this problem for so much time now that all the options have been explored. I mean, the feasible ones. But what is very, very problematic with the dust, at least with the lunar regolith, but it's very similar, the problem is very, very similar on Mars, is how sticky and cohesive this dust is. It's not easy to imagine it because on Earth we have different types of particles. We think, for example, about sand, and we know how sand moves easily on our hands when we touch it. But with the regolith, the situation is completely different. When I load a regolith simulant into my experimental setup, I have this little stick that I use to place the dust inside a tank, and every time that I load it, it gets stuck. It's a very, very tiny amount. I'm preparing an experiment that I do 3 times a week, and yet every time I struggle with the dust becoming whole attached to my little tank, and I cannot let it go inside it. It's the first time that I've experienced something similar. This type of granular material has a physics that is so complicated that it's one of the... I've seen a meme once. I've just started working on this type of things, and there was a rank of the most challenging types of physics, like what is more difficult, quantum physics, relativity, and on top of the pyramid there was granular materials. They are very, very hard to understand and very, very hard to work with. So with lunar dust and with Martian dust, we have this additional problem of the electrostatic charging. We have a radiation environment with the solar wind that is charging up the particles and the UV radiation from the sun. For example, on the moon, we have a positive charge side that is the one illuminated by the sun, and a negative charge side that are continuously changing during the lunar day, and causing a lot of interaction and transport mechanism between the dust particles, the positive charge side and the negative charge side. And those are all type of events that we don't see on Earth. We don't have a clear image of what's going on there. So yeah, these are the main problems with it. And I would also like to say that I work on lunar dust, and I know that there is another issue with the Martian dust that will come next. Like, we have to tackle the problem for the lunar environment. And then we know that we will probably use the same devices on Mars. But to go back on Earth, this type of devices, this type of mitigation technologies can also be applied on terrestrial application. And this has been done. Think about, for example, in a desertic and very dry area where you have solar panels. And those solar panels get covered in dust, for example, in a desert. At a certain point, it could become easier to use this type of mitigation technologies to clean the solar panels instead of just throwing water on top of them. And so what I want to say with this is that if we work hard to tackle the problem of the lunar dust and we find effective mitigation strategies, we will be able to apply them in the future missions. So it can be Mars, but can also be Earth. This is something very, very cool about rocket science and the science applied to the space exploration. We have a lot of people working on it, very smart people that come up with very nice solutions, very clever ideas, and then we can apply all those ideas to a lot of other applications. And Mars is one of that, of course, yeah.
Yeah. Now, are there any plans to test this out? I know that the Blue Ghost lander from Firefly Aerospace landed, and it had a version of this on board, and they were able to do this test. Are there plans to actually test these surfaces in space?
Yeah, of course. Blue Ghost, as you mentioned, has already taken an EDS device to the moon and demonstrated the effectiveness in the lunar environment. I know that there has also been an interaction, like a mission on the ISS to test how the materials react to the space environment. It all depends on the technology readiness level of the single devices, the TRL. We have to develop the technology on Earth and then slowly increase the readiness for that technology to, at the end, go to a real mission and be applied. What we're working on, for example, is a different type of material combination, and we are still at a lower TRL. We are still working on flexible devices that at a certain point will be tested on the moon. But I know that there is a lot of research on it, and that there will be missions in the coming years with different types of these devices, with different material combinations being tested on the moon.
Yeah, and I think people like NASA, as you said, is very aware and has been aware for decades that this is a gigantic problem, potentially hazardous to the health of the astronauts, definitely damaging to the equipment. They really want to solve this problem. And so, when people are saying the why don't they just, don't worry. Yeah, NASA is all over this and is testing out different versions of this technology in different places. And we hope that, hopefully we will see this go to the moon with a combination of other factors. Now, I've been reporting on one, like you can pour liquid nitrogen on someone on the astronaut suit, and that actually carries away a lot of it. There's mitigation to try and minimize the amount that falls onto your spacecraft. There's a lot. It probably will end up being just a combination of factors that all come together to just reduce the amount of that dust that makes its way into the habitat. Luca, what are you obsessed with right now?
So this is a very nice question. Right now, so I've just published this paper about this topic, about the EDS devices, and also want to, by the way, acknowledge all the co-authors of the paper and the NASA survey and the Clever Node that sponsored this research. But now that we have some functional devices that we have demonstrated how they work, we want to focus, at least I want to focus a little bit more on how to optimize their performance. We know that we need high voltages to make them work, but we would like to reduce those high voltages as much as possible. And we would like to optimize the performance by, for example, considering other variables. Right now I'm working on, for example, optimizing by changing the frequency of the signal applied to the device, and maybe trying to find not an optimal frequency, but an optimal combination of frequencies that can, for example, be more effective with a larger range of dust particles. So this is the main thing that I have in my mind right now. But at the same time, I think that to solve these problems, we cannot just focus on the mitigation side, but we also need to focus on the dust side. We need to understand better how the dust works. And this is very, very complicated. This is a very interesting topic. We have a lot of people here at Georgia Tech doing amazing work about this topic. So what I would like to focus a little bit more on is the science behind the lunar dust, how it charges, how the charge distribution compares to the mass distribution, for example. So those are the two topics that I keep as close as possible while going on with this research, so that I can keep both the engineering and the scientific sides on my side.
But it's interesting to me that you're focused on what is, when you think about all of the technologies, all of the things that will be required for some kind of human presence on the moon or on Mars. How are they going to eat? How are they going to drink? How are they going to manufacture supplies, making propellant, landing on the moon? There's a to-do list of thousands of things. And somewhere on that to-do list is deal with the dust, right? And you're helping fill in that check mark on that gigantic list. How does this work fit into your larger perspective about humanity's future in space?
So I'm a big fan of things that are done step by step. I think that we always need to add another brick to make the wall. And I always thought that in my life I wanted to just add another little brick. I just want to be part of it. I know that there are so many things to do to advance our understanding of the universe, our ability to explore it. And I think that if there is even a little tiny portion of it where I can give a little contribution, I will be very, very happy about it. So I think that this is the only way we can proceed in our exploration of the world. Every one of us has to do a very, very little part of it. The picture is so big that it's not easy to go so much in detail. But at the same time, when you're working on such a small detail, you need to try to keep the big focus, to see that you're doing a very small part for a bigger purpose, and it's something that you probably never see. I don't know if we will ever see, I hope so, but to see, for example, humans on Mars. I hope to see them, but you don't really know. You just know that you're doing a little part of the work that maybe in the future will help. So this is my view. This is how I see it in the big picture of human exploration of space.
Well, it's fascinating work. Luca, thank you so much for taking the time to chat.
Thanks so much.
Good luck with seeing your hardware eventually get tested in space. And yeah, someday an astronaut is going to set foot in their future station. They'll walk over the sill. They'll flick a switch. They'll watch the dust get pushed off the windows, off the sill of the door. They'll go, thanks, Luca. And then they'll go inside their habitat. Yeah, awesome.
Thanks so
much. Great to meet you. Take care. Bye-bye. That conversation with Luca Scifoni, I hope that answered some of your questions about how this technology is going to work. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nielsen, David Varabioff, David Gilton, David Matz, Evan Pro, Greg Feely, Hudson Ward, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Spitz, Michael Purcell, Monzo, Paul Robach, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. Well, this is good. I have been waiting to find somebody to interview about this very topic for a long time, and I don't feel like we kind of got right to the bottom of it. Luca is looking at it from his perspective and has less experience with what it's going to be like to move this stuff off of Mars, but still, that went a long way in helping me sort of understand what is the technology and how you have these multiple diodes and how you set up these standing waves and waves that are pushing this material. And it'd be really cool sometime in the future where, yeah, you've got some spacecraft surface and you come over and you flick a switch and all that dust just sheds off of it thanks to the power of static electricity. All right. I hope you enjoyed this conversation and we will see you next time.